starting. Okay.
Thank you. Thank you very much. Thank you very much to all the participants, and welcome to this new event from the Future Tech Week 2026. In this workshop, this is an interactive workshop revealing the story and principles behind SPIKA, a bio-integrated architectural prototype that blends art, science, and living systems, and shows how its regenerative design concepts can be applied on accessible, low-tech, sustainable building. I don't know if you want to start right away, Eski, or if you want to wait for a few more minutes to wait for other people to join. It's your call.
We can wait just 1 or 2 minutes more, and then I'm going to give the floor to my colleagues, actually.
Okay, perfect. Thank you very much, Eski.
You're welcome. Yeah, one more person. Okay, Liana, Camillo.
Yes, hello. I'm delighted that so many of you could join us today for our workshop on microbial fuel cells and advanced hydroponic systems. I'm Camillo Meinert from the Nogan Treaty Enforcement Agency, and right besides me is my colleague Dr. Reutener from the Vavilov Collection for Illegal Fruit and Vegetable Classification. As you know, for many years we have been detecting and dismantling clandestine farming operations on the territory of the Nogan Treaty that violate our ban on farming. So as for now, we have largely succeeded in the recent years in eradicating traditional outdoor agro-crime. But this came, of course, with the rise of sophisticated indoor hydroponic systems, because crime is now taken out indoors. Therefore, we believe it is essential that to study and understand the innovative methods that are employed by these illegal growers. We are honored today to present you some of the most outstanding experts in this field, several of whom have successfully transitioned from being prolific illegal growers to valuable collaborators on our side and support our agency with know-how now. But for this a little bit later. In order to give you a first and a concrete impression of just how difficult it can be to uncover these clandestine operations and to find these illegal indoor growers, our department has produced a short educational film about one of the most intriguing cases that we ever have encountered. It was called the Mihai Project, and it happened recently. Without further ado, I want you to present this film.
Usually the fruits came in from rogue nations outside the Nogan Treaty, like Hungary and Italy. Most of the stuff was canned or in some way processed. In some rare cases, we found fresh but tasteless fruits provided by some clandestine indoor growers in the neighborhood. There was absolutely no reason to grow these fruits. Our solar food program could perfectly provide all the nutrients and proteins using efficient fermentation techniques and return wasted farmland into precious nature reserves. People could eat everything in any form, but some people still insisted on the real thing, so much that they became criminals. Enforcing the Nogan Society kept us busy for almost 20 years. Spotting secret plantations via satellite, surveying smart meters and solar panels to find the indoor growers. A time-intense, but mostly successful endeavor, until this very special day All of a sudden, they were found on every corner, fresh, tasty, roots that were exposed to a microbiome. Someone out there was growing them in real soil and in vast numbers. We were checking satellite data, smart meters in every house, dugouts at cemeteries. Nothing. A little later, and with the help of our sophisticated interrogation techniques, we finally found out that all of it was closely related to a public laboratory. Their clients came from all traits of life: academics, workers, artists, even politicians. The place was run by a group of former scientists, life science, agriculture, most of them without jobs since we went post-vegan. They called themselves, and what they did, Mihai. Unlike ordinary fruit dealers, they were not into social credit points, but a different kind of currency. A urine for food program. We had to raid the place. Their hydroponic underground system was the most sophisticated our department had ever seen. They had created a microbial fuel cell that was able to make electricity from urine. Moreover, their bacteria digested the wastewater into nutrients to boost plant growth. Everything was transformed into a valuable resource. We found out that they totally had fooled us. Due to the taste, we had been looking for someone growing plants in soil, but they had established a root microbiome within their hydroponic system, giving their vegetables a natural taste. A great success for our Nogan task force, we thought. But as you know, lawyers. In court, they argued that due to the fact that their hydroponic system did not have any impact on the environment, it could not be seen as a violation of the Nogan Treaty. They came free. Today, they are making a fortune, turning sewage sites around the world into organic restaurants. Having the illegal vegetables issue solved by Mihai, resources are free for our task force to combat other crimes, yet unknown to mankind.
I hope you've been intrigued. Let's get into details. First, we invite PhD candidate Natasha Tate, who is an expert in MFC technology. Natasha, what are these MFCs and how do they work? Natasha, we seem to have some troubles with the sound. Do you hear us? We don't hear you.
Are you able to hear me now?
Yes, now it's fine. Thank you.
Sorry about that. So it is a type of bioelectrochemical cell where organic matter is used as the fuel, and bacteria inside the fuel cell will take the chemical energy from the organic matter and convert it into electrical energy. And these microbial fuel cells are the focus of research of the Mihai group at University of Southampton, where I'm working together with Professor Yanis Theropoulos and Dr. Dibiotina. To begin, the first MFC was written about in 1911 when Michael Potter showed how yeast can break down organic matter to produce electricity. And he wrote, "The evolution of caloric energy during fermentation or putrefaction is commonly recognized, and that electrical energy is also liberated during these processes is a conception of considerable interest. So today, more than 100 years later, a potential large-scale application of microbial fuel cells is in wastewater treatment. The idea being that you can take different waste streams, such as domestic waste, agricultural waste, industrial waste, and use them to extract the electrical energy using microbial fuel cells. So how would they actually work in SPIKA? How can they support a hydroponic plant growing system? Again, here the idea is that they will be fueled by waste, and the microbial fuel cells will generate electricity and offset the energy required by the hydroponic system, for example, for the lights, for the pumps, and for plant health sensors. Additionally, another capability of microbial fuel cells is that they can recover compounds from waste. And these are produced in a liquid form by the MFC, in a liquid that we call catholyte. And we are particularly interested in recovering compounds which are useful for plant growth, so specifically ions containing nitrogen, phosphorus, and potassium. So for context, human urine per day can have up to 11 grams of nitrogen, 1.4 grams of phosphorus, and 2.5 grams of potassium. So how does it work? How does an MFC actually produce electricity? So here on the right-hand side, I have a typical two-chambered MFC. So in the left-hand chamber, the anode chamber, this will be filled with wastewater, which is rich in electroactive bacteria and organic matter. And electroactive bacteria is simply a bacteria that can take an electron from inside its cell wall and transfer it to the outside. So these electroactive bacteria are going to be breaking down all of the organic matter, producing electrons, and growing a biofilm surrounding the electrode, which we call the anode. And all of these electrons that are getting produced are going to travel to the other side, to the cathode chamber. And this movement of electrons produces a current and allows us to power devices or store it in a battery. So one of the goals for Team MyHigh at Southampton is a benchmark of producing 1 milliwatt of power per 1 milliliter of wastewater supplied to a microbial fuel cell. So to do this, we are continuously developing membranes as well as the electrodes. So for the electrodes, we want them to conduct electricity or to support a biofilm for the anode and be good at reducing oxygen for the cathode. And for the actual MFC architecture, we are always developing as well. So in the middle, I have a typical sandwich design where there's 2 electrodes on either side of a flat membrane. But what we do in MyHigh is actually use a cylindrical design that you can see on the right, where the whole external surface, or almost the entire external surface, is covered by an anode, and the internal surface of the cylinder is the cathode. And this is really just to maximize the surface area that the biofilm will be in contact with the wastewater.
Natasha, what is this
Yes.
catholyte? How is it made? Is it different from the wastewater in what?
Thank you for asking. I'll just get onto that. Okay, so catholyte is produced because of several different processes in the MFC. So to begin, charge in all electrochemical cells should remain balanced. So as electrons are moving from the anode chamber to cathode chamber, there's also the movement of positive ions. So in the picture, it shows protons, but any positively charged ions will also be moving from anode to cathode to balance the charge. Furthermore, with the movement of ions, there's also a process called electroosmotic drag. And this is where water molecules are also dragged through the membrane. And finally, ions can also move during diffusion. So all of this leads to a buildup of liquid in the cathode chamber, and we call this liquid a catholyte. So it is water-based and rich in many different ion types. In our lab, we have been experimenting with different kinds of feedstock. So here you can see we have collected catholyte taken from raw sewage, and then catholyte also created from like a synthetic urine lab recipe that we have. And we have detected that we have managed to recover sodium, potassium, calcium, magnesium, nitrate, and phosphate. But we still have to continue our development of membranes as we want them to be really good at screening bacteria, but also allowing ions and water to pass through. So the idea is that we can control the pore size during the kilning process of our ceramic membranes. Another interesting property actually of this catholyte that we found is that they have antimicrobial properties, and this is down to two elements in that they can have high saline content just from the sheer amount of ions making salts, and then also they can have quite a high basic pH, which inhibits the growth of bacteria.
Could I ask you one more question? Going back to the electricity output, to the energy.
Yes.
It sounds like it's a very low energy output. Is there a way to scale up MFCs to stack them together?
Yes, thank you for asking. So to maximize both power and catholyte outputs, you can combine many MFCs together. So traditionally, you might think like, why don't you just make a really giant MFC? But actually, it's best to, again, maximize surface area. And you can do this by combining many small cylinders together in one tray. So they're all sharing the same wastewater, but the surface area that biofilm will be in contact with the wastewater will be increased. So in one tray, you have a lot more current being produced from the biofilm compared to just one MFC. And then you can stack many trays together and connect them in series to boost voltage and current. So then you will have a stacked system. You can extract all of the catholyte from the many cylinders to feed the hydroponics and use that combined electricity to provide for the lighting. So here in our lab, we have experimented with this. So on the left, we have an example where we had raw sewage just flowing down into two MFC trays. And then the sewage was just continuously recirculating through the two trays until the organic content had been greatly reduced. Then we just start the process again and replenish the sewage. And here in the center of the slide, you can see that catholyte is starting to build up in the cylinders, so then we can extract that. And I will just show here a video also. We were able to power this 5-volt LED strip using this another stack design here. It's actually 12 MFC trays combined together. And here I just have some data to show that the maximum power for the trays is around, for the sewage-fed system, can be between 19 and 15 milliwatts. And for the synthetic urine, which has a higher organic content, it's between 22 and 19. So this is, as you can see, much greater than a single MFC, which we are aiming for 1 milliwatts. So we have managed to improve the power output. And then we have taken that design that I showed with the 12 trays, and this is what we placed here in SPIKA. It was inoculated there in Milan using bacteria from a denitrification tank as well as soil. And then we fed it with our artificial urine recipe, and it's looked after by students from Milan Polytechnic. And we were collecting data from there throughout the months that it was operational, and it had maximum high voltage of around 3.8 volts. In this case, the MFC system was not integrated with the hydroponics at the top of the tower, but of course that is our goal moving forward. We want to continuously improve cathode production and as well as electricity production. So thank you for listening, and if anyone has any questions, I would be happy to answer.
Thank you very much, Natasha. I think let's open the questions to the audience.
Maybe we can add that if you have any questions, you can also type in the chat during the presentation, so we can read it from there.
Let's wait a bit for somebody typing, and then we will move on to our next expert. I can see one hand raised.
Yeah. So hi, I'm Maria. I'm from a Royal College of Art, biotechnicians in natural matters. So I'm like also interested in to find out, you know, maybe the electrical output of one MFC is like tiny, but then I saw, you know, you put it in the stack. Is there also any other like additional electronic circuit that is required to boost up the power output so we can power up like higher powered electronics?
Yes, so actually, combining MFCs is just one way of improving power output. So as you suggested, that you can absolutely use power management circuits to basically track what is the maximum power and then find those ideal conditions for the bacterial community and only extract power when it is in this state, and store it in a battery, and you can use power boosting chips as well included in this circuit. And then there's other methods for improving the power output, which I didn't really go into great detail, but there's a lot of research into electrode materials, membrane materials, and then just how you shape the microbial fuel cell in general that can greatly improve the power output.
Right. Thank you. Yeah. Well, maybe I can also asking some questions like when you are putting the system together and also like keep maintaining it, you know, do you face any like challenges in maintaining it? So because I know, you know, you need to feed it from time to time the substrate or the, you know, the artificial urine. Like in practically in real life, you know, how do you find this process?
Yes, so when we are in the lab, it's much easier for us to access it and do all the maintenance. But of course, we face issues like with the biofilm growth. Sometimes it can grow to an extent where it is might cause a blockage, or we might see some corrosion in the wires. So these are just things that you need to keep checking on a regular basis, which is, yeah, as I said, easier for us in the lab, but in the actual SPIKA, it was much more difficult for the person looking there because it was encased within the structure. Yeah.
Yeah, it seems like I have a lot of questions, but I'm like really interested
It's
in,
great.
you know, building such system too. So there, you mentioned there are some corrosion in the, maybe is a connection wire. There are some people using like copper wire, you know, which is just like a jumper wire we usually use in the electronics. But I tried to make one before and then it got like corroded. Like you can see that the copper wire corroded, and I changed to stainless steel wire. Well, at the moment, it still doesn't have much a big problem, but I also see, like a lot of research paper using platinum, is it like platinum wire? I mean, would it affect the performance of the cell, or which is have you tried different materials for the electrical connection, and what is your suggestions or advice in using this material, the material selection?
That's great that you've tried a lot of things. Here in our lab, our standard material for wires we use is nickel chromium wire. But yes, different types of wire will corrode more easily. And it also depends on how often you feed the microbial fuel cell. Like if they're not getting electrons from their substrate, they will just start to eat away at the wires. Yeah.
Yeah. So it's better to keep it to connect to external resistor to lower the corrosion rate. Am I get it right?
So we are using the external resistor to connect the anode and the cathode. That's what the purpose of the load is. Yeah.
Yeah. Yeah.
Thank you for the engaged discussion. We actually are very much on time, so if you have more questions, feel free to ask or always write them in the chat. We can always come back to them in the end.
Thank you.
I see one raised hand, Ezgi.
Yes, I just wanted to add, Maria, that yes, some research groups are using platinum wire also, the different type of wires, because she was trying to, I think, mention that. And also I think keeping the analyte solution fresh and nutrients abundant would be nice. I mean, would be beneficial for the exoelectrogenic bacteria growth and also the electricity production performance, right? That's my question to Natasha.
Yes, yeah, you're right. Yeah, so like they need to get their electrons from somewhere. If they're not getting it from the substrate, they will just take it from other metallic sources.
And how long, if you use it as a batch mode with the urine or the sewage or whatever analyte you're using, how long can they continue to produce stable amount of current without changing the analytes?
Okay, if there is not some other issue like a clog or some other fault, like we have had really long running MFCs in our lab lasting for months, or even Professor Yanis has an experiment that's now running for years. Yeah.
Is it fed batch or is it running?
Yes, that one is a continuous, but our trays are also kind of semi-continuous, semi-batch fed. Yeah.
Okay. But consider you are just using a batch reactor, you are feeding once and you don't touch it. Can it work like a month or a week, or what's the lifetime without making the system continuous?
Have a batch and you just want to see how long you can feed it. That will depend on how nutrient dense it is. But also within an MFC, it does help if you have some flow happening within, yeah. So it really depends.
Mixing, yes.
Yeah. Depends on how rich is your media and actually how developed your biofilm. If it's a very developed biofilm, it will very quickly digest all of the organic matter in there.
Okay, thank you very much.
Thank you very much, Natasha. Let's move on to our next guest. We invited Dr. Mukesh Sharma, who's an expert in hydroponics.
Hello, everyone. Good morning. Am I audible? Perfect.
Yes, we can hear you really well.
Yeah, so I'll share my screen. Okay, so can you see the screen?
Yes.
Perfect. Okay. Yeah, so just a second. So can you see the screen? Okay. So I work at University of West of England with Professor Neil Willie and Shagun. So we are based at School of Applied Science, University of West of England, Bristol. So I hope that most of you must have heard, read, or somewhere watched, some videos or some information about how the hydroponics is developing. So if you can see from this graph, so hydroponics basically evolved like anything. So in 2015, it had global market of around, I would say, just 30 million USD, which increased to about 12.5 billion USD globally by 2025. And if we talk about Europe and UK, so it rose from something less than 15 to 20 million to right now it's about sorry, is about 315 million USD market. So hydroponics market has evolved like anything, you know. So what is hydroponics? So hydroponics is basically a type of horticulture, basically a subset of the hydroculture, which involves growing crops in absence of soil. So usually the crops are grown in water-based nutrient system in artificial environment. So this is the image that we have from the setup that we have in UV Bristol. So I'll discuss in detail about this setup in the further slides. So let's talk about the history of hydroponics. Although it looks like a very new technique of growing crops, but much before the modern chemistry, the ancient civilization explored how to grow crops in water-based, nutrient system. So it is said that, or it is mostly cited that about in the floating gardens of sorry yeah, hanging gardens of the Babylons were the first where people started learning growing crops using hydroponics technique. It was around 600 BC, and then followed by the Aztec Chinampas. And in 1929, Dr. William, who was a professor from UC Berkeley, he was the first person to coin the hydroponics and to prove that the plants grown using the hydroponics techniques are commercially, they can be grown. uh, he successfully grew a 25-foot tall tomato, plant just using the nutrient solution. And then after that, there's no stopping. So there have been a lot of studies by different, universities, research centers, and even the NASA is also involved in, growing plants using hydroponics techniques, and just to check whether this can be, done in space to grow food over there. So, what are the merits of hydroponics? So, the first and the foremost important thing is water. So, hydroponics techniques makes efficient use of the water. It usually takes 80 to 90% of less water as compared to the traditional soil farming. Plants grow faster, you know, and higher yields due to the controlled environments. So, the most important thing, the other thing is the space utilization. So because it is done in the controlled environment, it utilizes much less space as compared to the conventional farming. It reduces the pesticides use as the plants are grown in the controlled environment. It enables continuing farming throughout the year because it's done in controlled environment and in a proper protected space. So that's the case. It reduces the land size and minimizes soil degradation. So, how is this hydroponics against the principles of the agroecology? First and foremost thing is agroecology involves, soil and animals and other things. But in case of hydroponics, it is the absence of the soil, which breaks the link between the rhizosphere, farming, and natural ecosystems. It reduces the biodiversity, and hydroponics techniques involve high tech, high technologies, which is not in the case of agroecology. It's high energy consumption process and conflicting with the agroecology's emphasis on minimizing ecological footprints. It has social disconnect and then nutrient cycles. So, how are hydroponics managed? And mostly we say that the plants grown using hydroponics techniques are spoiled plants. This is because they are fed with all the things that they need. The sufficient amount of nutrition is provided. They get sufficient amount of light, and we keep on manually refreshing the solutions regularly. We solve the pH, and conductivity and other drifts, and then it uses short growth periods annual plants. So much potential to match the resource supply to demand management algorithms. A need to change source of nutrients waste biological aids. A need to extend the refreshing interval of solution, use X-rays, stabilizes pH and everything. So this is why we consider that mostly the plants which are grown using hydroponics, they're spoiled plants. Although they look, big, greener, but they are they taste not the same as the plants grown in using the soil system, and they have a bit less nutrition as compared to the plants grown normally. Let's discuss briefly about the microbial fuel cells. As you can see in the screen, we have a two-chamber microbial fuel cell. So what happens basically? We feed the wastewater in the anaerobic in the anode chamber, and the anaerobic digestion of the organic matter takes place. And during this process, the protons pass from this side of the chamber to the other side, and to balance the energy, the electrons flow through the external circuit and we get the power. So microbial fuel cell does two things. It treats the wastewater and it also generates the electricity. So in my high, what we do is we are using microbial fuel cell to treat the wastewater. At the moment, we are using sewage waste, and we are also generating electricity using this. So the electricity generated from the microbial fuel cell, we are using it in the hydroponics for different requirements that we have. So yes, so this is what is we are doing in my high.
Dr. Sharma, can I ask you, you're using this catholyte as feed for the hydroponics. How do you use it? How does it affect the plants?
Yes, thank you. Yeah, thank you so much for asking. So, normally what happens, we provide inorganic nutrients to the plants, but what happens in the case of microbial fuel cell, we are treating the wastewater, and we are trying to replace the inorganic nitrogen with the organic ones, right? So the catalloid that we obtain from NFC, we use them to provide the nutrition to the plant and replace the inorganic nitrogen that we have. So these are the findings that we have from our recent research. As you can see here, we have grown basing plants with variable composition of the catholite. We have mixed, so we have done, as you can see, we have done three experiments. The first one goes with the grow stream, where we have just H1 is the one where we have used 75% catholite and 25% soluble solution. In S2, we have used just a soluble solution, and in H4, in H4 we have used 50%, 50% catholite and then 50% nutrient solution. So you can see this is how this is the mean area of the leaves, and this is the perimeter, and this is how the root and the shoots have grown in different growth streams. So as you can see that in case of when we are just supplying the soluble solution, the mean area and perimeter of the leaves is, they are much bigger than the one which are grown in H1 and H4. And the same is the case with the length of the roots and the shoots. Yeah, so because we are just providing the soluble solution, so the roots are going much taller, and so are the shoots. But as we can see from the figure, when we are providing about 50% catholite and 50% soluble solution, the plants still look really, really good. So the root, the length of the roots and the shoots is almost comparable to the one which is grown using just a solvent solution. And also the mean area and perimeter of the leaves was almost similar uh, in many cases, I would say, because if you see here, we have S2A, S2B, S2C, D. So in a single grow stream, we have provision to plant 10 pots. So this is the data for all 10 pots. So if you see on average, so the perimeter of the leaves was mostly the same, and also the root and shoot length was comparable. So we can say that 50% catalyte and 50% solution works fine for the plant. So where we are up to, the growth model predicts. So this is a growth model of the basil plants with sufficient nitrogen supply just from the solvent solution. So this is just one growth curve of the plot that we have, right? So as you can see here, the growth model predicted a growth rate of about 0.21, assuming 4% nitrogen of dry weight, and demand peaked at 6.2 milligram per day on day 37. So what's the conclusion? So integrating hydroponics with MFC could pave the way for sustainable farming in the future while controlling carbon nitrogen pollution and sewage management.
Dr. Sharma, hydroponics are criticized for being really energy inefficient. I understand that you are substituting part of the energy with MFCs, but do you do anything else to handle the high request of energy for the system?
Yes, thank you so much for asking, Uliana. So the current setup that we have at the University of West of England, we are really focused on optimizing the power consumed. So basically, in case of hydroponics, uh, a lot of power is consumed to manage, the water circulation system, the irrigation system, and other things which are involved during the operation. So what happens? What we are trying to do now is optimize the light algorithm. So as you can see here on the screen, we've got this rayon lights. So what is the best thing about these lights are we can vary all the spectrums, and then we can optimize the power consumed with the light, because light, water circulation, and aeration, these three are very, very important, and they consume a lot of power. So we are trying to just see that what could be the optimized amount of light that we can have for growing basil. And so we are trying to reduce the power consumed not just by the light, but also what we are doing is we are trying to focus on circulating the nutrient solution. So we don't want to keep on the pump all the time. So what we are doing is we are just placing some timers, and then we are providing we are switching on the pumps, aeration pumps and the water pumps for a specific time intervals, so that we can control the entire energy consumption thing. And the most important thing is, just like our colleague Natasha said, that we are producing some good amount of power using the microbial fuel cells. So what we are doing at UV is we are trying to design a system in such a way that we could fulfill most of the energy requirement from the energy obtained from the microbial fuel cells. So there are different sensors involved. There's the light that we have, I'm showing. So we are trying to design the entire system in such a way that we can fulfill the maximum energy requirements with the microbial fuel cell, or maybe if needed, then we can, complement the energy requirement with the renewable sources of energy. Yes, so this is how we are working on this. So this is like we have presented our work in different places, and the most important one at the moment that we have is in Milan Trinale. So I have discussed about the setup that we have installed at the Milan Trinale in this video. Yeah. Ezzy, can you play the video for me?
I'm playing.
Okay.
Just a second. Yes. Sorry.
Should I stop
I will-
sharing my screen?
Oh,
Okay.
it will happen now.
Yeah.
Just a sec.
In our studio, we don't really have the sound.
Yes.
You
Yes.
don't hear.
I don't think we'll sound. Yes.
Maybe you can try share.
Okay. So let me try. Let me try doing myself from here.
Yeah.
Just please let me know if you can hear the sound. Can you hear the sound?
No, we don't have the sound.
Okay. So
I will try one more time. Just a second.
yeah, please. Here. Hello everyone, my name is Mukesh Sharma. I work at the University of West of England, Bristol. So today I'm going to give you a live demonstration of the hydroponics tower. So this is how a hydroponics tower looks like. We had a similar structure installed at the SPIKA at Milan, Finale, Italy. As you can see here, we have 7 layers and each layer contains of 8 holes where we can put pots, and this is how you can see we just started growing some basil plants. So you can see here that they just started sprouting out, right? And if you see here, you can put total of 56 pots, right? As for a requirement, we can reduce a layer or maybe we can increase also. So when we buy, normally we get about 8 layers. So we have a provision of placing around 64 pots, but we can vary as per the requirement. At the bottommost part, you can see here, this is a 40-liter tank. So what happens basically, we can fill this tank with 40 liters of water and we can mix the nutrient solution as per the requirement. And this one, as you can see, is the lid. So we can open the lid, fill the water and then close it as per the requirement. And to show you that how the water cascades from the top to the bottom, let me just open the lid for you. So when you open the lid, as you can see here, we've got these pots where when the plants grow bigger, the roots come out from this. So this system, what it does is it provides water to the roots, and through these tray kind of structure, you can see that the water cascades down to the bottom, right? And it gets recycled. So this is a very intelligent system made in this hydroponic store, which really makes it very useful. At the moment, I'm just for the demonstration, I've just connected indirectly without any timer or anything, but we can time the pump as per the requirement and the way we want to provide the nutrient solution to the plants. So this is the hole made to the tank so that we can connect this pipe to a bigger tank, which gives us a flexibility to provide the nutrition to the plant for a longer duration of time without worrying about the tank being empty. So we prefer keeping the tank closed all the time because we want the plants roots to be in the dark. So yes, this is the demonstration of hydroponic farm. Please feel free to ask any question which you may have, and just in case if you want to know in more detail about how this hydroponic store was installed at SPIKA at Milan, Italy, please visit the link which I mentioned in the slide below. Thank you so much. Take care. Bye-bye.
Thank you very much. Dr. Sharma, that's been a great
Thank
video
you
as
so
well.
much. Thank you so much, Eji, for playing the video. Really appreciate it. Thank you.
Let's open for
You're welcome.
questions. You can simply raise your hand or type them in the chat.
We have no sound. Okay, it was before.
Any questions about hydroponics?
Natasha.
Natasha?
I have a question as
Yes.
why exactly is the main focus on basil, like compared to all other plants?
Thank you so much, Natasha, for asking this question. So at the moment, we have just started with the basil, right? And we also have plans about introducing other crops. So at the moment, we are just doing with basils, and we'll be moving on to other crops in some time. Thanks so much. Yeah.
Professor Neil has a question, I think.
Well, I was just going to add to Mukesh's answer that basil is the crop across Europe that actually has got the highest proportion grown in hydroponics. Most of the basil that people buy and use is grown in various sorts of hydroponic systems. So hydroponics is very important for basil growth.
Thank you so much, Professor Neil.
I have a question about you're testing the Catalyte solutions, 50%. Yeah. So it is, of course, less than Sonofel solutions biomass, I think, at the end. The diameter and circumference, I think, of the plants.
Yeah. Okay, so we have mean area, mean perimeter. Just a second.
Maybe you can
So do you want me to share the slides? So it's mean area, perimeter, and root shoot length. Do you want me to share the slides, Saji?
Would be good. Would be good. We can.
Perfect.
Yeah. Check it.
Yes.
Yes. So is it how can I say? Is it statistically significant difference between the only Sonofel solution growth and 50% Catalyte, 50% Sonofel solution growth? Because I think even though it's less than Sonofel, it's still high enough to consider significant growth, right? That's my question.
So if I'm right, then you're asking that why I'm varying the composition of the catalytes and the nutrient solution, right?
I'm asking actually, can you observe a significant growth with the 50% Catalyte, 50% Sonofel solution, even though it's less than only Sonofel? Could you accept it as a significant growth, and would you, for example, go for it to grow your plants with these earlier results?
Yes. So what we did, we had 4 growth streams. The first one we grow with 100% solvent solution. Then the other one we mix with 50% nutrients solvent solution, and then catholyte. Then we increase the catholyte to 75% and kept the nutrient solutions to just solvent solution to 25%. And in the fourth, that if you observe clearly, then you can't see S3 over here. So S3 was the one where we use 100% catholytes and no solvent solution. So what eventually happened is in S3 the plants didn't grow. I mean, they grew really, really small. So as compared to these, and they were negligible. So we don't have data for that. If you understand what I mean. So yes, and also when I grew plants using 50% catholyte and 50% nutrients soluble solution, and in the growth stream when I use 75% catholyte and 25% soluble solution, we can observe visibly from the leaves that the plants felt some kind of toxication, right? So there was some toxicity. We assume that it was sodium toxicity, and to mitigate that, we have also done experiment using gypsum, right? So we introduced gypsum just to see that if we can mitigate the toxicity by this catholyte. Actually, it does, right? So it did. So we don't have image for that, but we tried testing that, and we found that yes, the toxicity was visible from the leaves, and we tried to resolve this issue using the gypsum. So yeah. So I hope I'm able to answer you, right?
Yes, I think we can clearly see that they are showing when you add the catalyte solution,
Yes.
Plants can still grow. So
yeah, but the plants were really very happy from 50% catholyte and 50% soluble solution. Yeah,
yes.
That's right.
Thank you.
Thank you so much.
I guess let's move on. Our last guest for today is Yannis Munt, who is a PhD candidate in regenerative architecture and working on design of SPIKA in a team of designers in Rachel Armstrong's studio. Yannis, could you tell us a bit about the process behind the design of SPIKA, how it came to be?
Yes, thank you for giving me the word. I'm happy to be here today, and everybody, thank you for coming. I will briefly introduce you into how all of these very interesting technologies were like integrated into a more like narrative-based design. As for the installation of SPIKA, it brings the idea of a living architecture into more like architectural practice. It exposes how fragile nature is within our built environment and points to the need for like more maybe political responsibility in protecting it. Now, drawing on microbial structures, SPIKA takes on an intentionally intimidating form. It shields plants and natural systems, allowing interaction only at a distance, while protecting them from human interference. The structure is both mythic and microbiological. It acts as a guardian of the delicate biological interactions within, and at the same time as a warning that our relationship with nature must be rethought. Through its defensive form, SPIKA asserts the autonomy of nature and its deep connection to technology, showing how microbial innovation can help restore ecological balance. Structurally, SPIKA protects the plants inside its 6-meter tall thorn-like body. Its form refers to the bacteriophage, which is a precise geometry and defensive protein spikes. This creates a protective barrier that prevents the disturbance of the complex plant-microbe relationships forming inside. This microbiology continues in the tower's internal electrical circuits inspired by e-pili protein nanowires that enable interspecies electron transfer.
Yannis, I think the first impression of SPIKA is that it looks really hostile. Why is it like this?
It does look hostile, and it's because kind of friendliness became a trap. For decades, nature was framed as accessible and benign, something to touch, optimize, and extract from without any consequences. So SPIKA breaks that agreement. Its hostility isn't aggression, it's refusal. The form enforces distance because unlimited access has repeatedly proven destructive. Protection comes before participation.
And if I can ask another question, because we just discussed all the
Yes.
technology that is inside of it, and it just sounds like it's so many details and elements. How do you even design anything that combines everything like this all together, something so complex?
Indeed. To bring all these technologies together, we like to work with a narrative-based design. So we came up with a story behind the installation itself. And if you bear with me for a couple of minutes, I will guide you through a part of our story. So if you carefully listen, you might get the point. It's a story about a cleaner. The cleaner moves through the corridors of the city, a figure wrapped in quiet motions and veils of scent, citrus, bitter lime, the muttered tang of antiseptic. Each night, she's sent to scour, to purge, to press the halls of offices and museums into a silence unbroken by the life they hold. Her hands, some say, do the work, scrubbing, sweeping, making it new. But there's another work to do, known only to her, a secret lineage passed through agencies that know the hidden spaces, the stitched warmth in the carpets, the gentle dust humming beneath the tiles. She has learned, as her ancestors had been obliged to learn, that true work is not always in what the hand removes, but in what it allows to remain. Each night, with cloths and sprays, she enters the familiar tension, the endless tug of war between sterility and survival, between what she takes and what she leaves behind. She has made of herself a visitor, a conductor of spaces between, neither ally nor enemy. And in these spaces, the unseen architects, builders of invisible cities, wait. Not that they would call themselves builders. They are makers without a name, inhabitants bound to no calendar, to no day or night, silent, steady. They nest in crevices, knitting networks with a quiet insistence. Here, where light does not fall, where dust rises and settles. They construct, bridges gaps, weave ancestral paths. Wherever the cleaner wipes, they reassemble. Wherever she brushes, they return, more stubborn each time, resilient as an ancient rock. Each tool, each cloth, each stroke of her hand, they feel her intention, her unspoken terms. They yield, they reform, slow and eternal, casting fine threads and filling cracks with lives too fine to notice. Too many to shame. She knows that no brush could ever reach them all. No solvent could ever scar them away forever. Dust motes, spores, a lattice of tenacity, they persist without word or resistance, fading, then glimmering, each time softer, stronger.
Who is it that SPIKA is protecting?
That's a good question. And SPIKA protects like living systems that collapse quietly under constant access. Plants reduced to commodities, microbes erased from architectural logic, and ecosystems treated as background. Indirectly, it protects humans as well by forcing restraint, by setting boundaries around life. SPIKA challenges the assumption that dominance equals care. To go back to the cleaner moves through the empty exhibition rooms and office corridors, bound by her unseen pact with the sprawling megalopolis below. There is a balance to be struck. Surfaces may be polished, but not bare. Corners can be clean, but with space for roots. This is her art, her practice, to cleanse yet not to vanquish, to leave room for what is hidden, to keep on. In the end, she knows this dust, this soil, this quiet and unyielding life will endure when her bruises have faded, when her solvents have dissolved. She knows that if the city stewards look close enough, they might decry this art as herstory, witchcraft even. In their view, a clean is a clean and sweep is a sweep, but she calls it something else, a quiet tending of a mysterious garden hanging under the glassy gleam. This is why each night she packs her plastic relics in this corner, her breath steaming in the night air, knowing that on her departure the builders rise, deep within the stone, ready once more for their daily bloom. Thank you for listening. So
Thank
as
you
you
very much
might
for this
or might have
beautiful
not,
reading.
I'm sorry?
Thank you for beautiful reading.
Thank you. As you might have understood or not understood, so about the story about the cleaner exhibits as a gatekeeper between like the interconnected worlds of SPIKA. It mediates a bit between the relationship between like the tower and the thorns and the technology. You have the MyHigh microbial platform, the hydroponic plants, and the public. So she's like a bit, or he is a bit like positioned between humanity and nature, and she protects a bit the tower inner ecosystems by monitoring boundaries, mainly like through regulating like microbial presence, which is like the things that grow overnight that we don't fully want to remove, but they have to be there. We have to have like some kind of cohabiting relationship with them. So this would be the role of the cleaner. Next to the narrative that came with SPIKA, of course, we also had to build it. That's also struggling for a second to go to the next slide. Okay, it was stuck. So then there was the framework. We of course had to build it. So we came up with a 6-meter tall structure. We started with like the basic frame, and then at the bottom you can clearly see where the hydroponics and the microbial fuel, mainly the microbial fuel cells took place, and how we gave like this bacteriophage tall spiky structure form. In the middle you see the bioreceptive panels, which I will come back to in a second, and then indeed the hydroponics on top. This is a bit of a drawing that like shows better how the whole structure was built up from a very pragmatic designer approach. And this is then the image of the final tower. Then my colleagues from the research group, they did amazing work on bioreceptive panels. They each have their own material, which goes from wood and clay to concrete. They designed like very specific geometries with like well thought cavities that are currently being like researched upon, like which are the most beneficial for microbial growth. And then for this installation, they went to a river nearby where they collected like local water to inoculate the panels with. So there would be like a microbial growth from like a more local ecosystem. Then last but not least, as an additional design to the tower and the narrative, there was a second narrative that was the parasite. That actually also symbolizes a bit like this idea of like symbiosis, or like the holobiont, where like an organism lives on top of another organism and can be a host, but can also be a parasite, or both at the same time. And there we designed, excuse me, we designed like a sculpture that was like digitally sculpted. And then of course we always like to experiment with 3D printing. So from an aesthetic point of view, we thought it would be interesting to also try to print this sculpture. So then we ended up cutting it into multiple pieces, as like large scale 3D prints are still not as easy as you might think. so this was a bit the approach, the method to 3D print the bigger sculpture. That's it. Thank you so much for listening.
Thank you for this hypnotizing talk, Yanis. Let's open for questions. Ezgi?
Yeah, maybe I can start, then hopefully we can have other questions. How tall or how big was the parasite, Yanis? Because I can see there are a lot of small pieces, like a puzzle. You put them together. It would be interesting to know how big was it on top of the SPIKA. Yeah.
So if it was mainly on the maybe I go back to a render, where you can clearly see. So this gives a a better impression of how the parasite was actually connected to the tower, and it was printed in two parts. So one part was around like 70 centimeters by 1 meter, and then the second part was also around like 80 centimeters by like more like 30-40 centimeters. And of course, when we print, this is in a PLA print, which is sadly we're still a little bit limited when it comes to biomaterials to make this kind of sculptures in PLA. So we had to print on like printers from 25 centimeters to 25 centimeters or 40 by 35 to make like all these components. I think in total there were like 80 components to come to this kind of scale of 3D print.
Ooh. 80.
80, yeah, which then individually had to be glued and connected. So yeah, I definitely had fun with it. So
yeah. Must be very hard work. I can.
Yeah, a lot of sticky fingers. I'll put it like this.
Also finding the right glue to connect the printed material.
Exactly. Yeah, some glues interact better. You get like a kind of cold welding by a chemical reaction of the plastic with the glue. So of course, if you want to make these things load bearing or structurally, you have to think about this, because once the seam break, then your whole structure is basically useless.
Yeah. I think Uliana shared the SPIKA website on the chat. If you're interested, you can check it. Any other questions? Natasha?
Yes, I just wanted to ask, I think the design of the parasite is really, really amazing. I just wanted to know, did you come up with that just entirely of your own making, or is it based on like an actual living parasite? Does something really look like that in the real world?
There was definitely some. At first, like it's a design I sculpted myself from scratch, but of course, as every designer, you need some inspiration. And together in the narrative of SPIKA, at first, we believed that this kind of hostile medieval structure could use a similar approach as to churches or as Catholics, where they use gargoyles. For anybody who doesn't clearly remember what a gargoyle was or is, it's like the little creatures that protect the church from evil and that also divert the water from the church, which then resembled a bit like this mythological creature that is also in symbiosis with the building by diverting the water, but also protecting it from any other things that are not allowed. And this was a bit the starting point. And because we were talking with like microbial technologies and architecture and living architecture, this got translated into then a parasite that would resemble something similar. So I hope that's an answer to your question.
Okay. I cannot see any other hands. Okay. Is there any remarks, closure remarks, Rihanna? You want to announce anything or share?
I think first of all that in spring we will be announcing the DIY competition that works with MFC technology and ways to apply it. It will be a DIY and we will have several teams compete. We will have a hands-on event and we will also have several months of kind of preparation. I'm going to post a link where you can also see the news soon, hopefully published. And the website that I'm sending is also the MyHi website, so you can read a bit more about it, see the names of our, all of the professors and people participating in it and all the institutions. And hopefully soon you will also be seeing the video that we shared in the beginning there in the video page and learn a bit more and see also our professors and our, students and everyone kind of also giving a talk in a similar style and also some tutorials.
Thank you. Thank you very much for the information. Camillo? You
Yes.
don't have. Would you like to say anything? Okay.
No.
Maybe for
So-
the video, have you shared the first video you shared with us, the website of
Yes.
the.
We can share this video as a link on the website Ulla mentioned, so the website is ready.
Mhm.
So
Ah, okay.
maybe we can just write it in.
Mhm.
It's MiHi/Organic.
Mhm.
Because if you enjoyed the first video, there are a few other detail
Yeah.
of the.
So it's like a
technology.
landscape. It's like a landscape you can explore with
Mhm.
written information as well and pictures. So
It's now in the chat.
it's on the chat.
Yes. If you want to click on or copy the links, please do so, but maybe we can email afterwards the meeting. I think we are good. We almost finished a little bit earlier, so we are good at time. Cesar, how was it? What is your thoughts? Maybe we can ask you some questions.
No, I just wanted to say that it was a fantastic presentation. It's what we were looking for, also together with the European Innovation Council. It's just like it's presenting difficult concepts that puts together different kind of like professions inside. So the fact that it was regarding science, regarded just like the part of agriculture, regarded the part of architecture, and all in a sense of collaborative and sustainability. And it was like it was really a pleasure. Also, how you framed the presentation for me was like inspiring. So every single intervention, every single presentation that all the speakers did, it was for me enlightening. Not being an expert on this matter, so I appreciate the event. I really appreciate of getting to know each one of you. Eski, thank you very much also for also organizing everything. For us,
No, anything.
it was fantastic. So thank you very much.
I mean, you should thank Uliana, Camillo, Yanis, Natasha, Mukesh, and other my all colleagues because it was their idea and it's fantastic. Actually, I really found it so interesting and nice. I think, is there any problem to access the Organic website because it works for Jill, but it doesn't work for Christian. I can see in the chat.
Yes, we see it. We are working on it. I don't know why it didn't work. I made it available today.
Okay.
For
It
some
works for
reason
me.
in my browser it worked, but Yeah.
I think we will publish a news on the MyHi page with the link properly, like
And
today or
then you can
tomorrow.
enter it. Yeah.
Yes,
Okay.
but thank you for calling it up. We didn't see it from
Yes.
the back end.
Yeah, it's good to know if there is an issue still or not. Okay, perfect. Thank you very much for everyone joining. And if anything, if everything, everyone, yeah, okay. Christian, would you like to say anything? Yeah, okay. I can see you turn on your video. No, if nobody has any other points or questions, maybe we can close this workshop. Thank you for joining.
Thank you very much.
Thank you.
Thank you.
Right, thank you.
Thank
Thank
you.
you.
Bye-bye.
Bye-bye.
Bye.
Bye.